Right, a university degree paper on multivariable calculus. Question 1 on partial derivatives and partial differential equations. 20 marks altogether. First part for 4 marks is just find the partial derivatives. You've got a function in terms of two variables x and y, which forms this product here, and it's just a case of first of all differentiate it with respect to x, leaving y constant, and then respect to y, leaving x constant. That should be easy enough. Right, here we go then. So there's two variables, first of all differentiated with respect to x. But first of all, the product here, but first of all it's well to remember that if you've got the derivative of a square root, the answer will be just 1 over 2 times the square root. That saves messing about, changing index and radical form. Right, so back to this then. So this is a product. So first of all differentiate that and leave the root alone. And then leave that alone and differentiate the square root, which will be 1 over 2 times the root. And on top, the derivative, which lives by the 4x cubed because y is constant. I can just write this out a bit neater because I can do the 2 into the 4 is 2 and add those powers to make x to the 6, leave that alone, which could do as the answer, but I'll put the two terms together, take out any common factors, that x squared and that nasty root underneath, and that leaves everything else inside neat. So I've got 3, and with the root out, I'll be back just to the thing itself on top, and then 2x to the 4. Tidy up this part after it, x squared over that root again, and within here I've got 3x to the 4 and 2x to the 4, so that's 5x to the 4, and then that's 15 y squared, there we go, and then we go, oh, another common factor to come out, 5 can come out, 5x squared over that root times, and all I'm left with then is x to the 4 and 3y squared. There, and that's that one done. Right, next derivative is even easier because there's only one mention of y. There it is, lurking inside the root, and there's not even a product, so that's just a constant. And again, the root, that's 1 over 2 times the root. The derivative of that will be 10 times y. Tidy that up, 2 into 10 goes 5, 5x cubed y over the root. And there you are. Easy. Right, in the second part, again there's a function expressed in terms of two variables, but this time in its expression there's another function which is expressed in terms of just one variable y upon x, which means that when it comes to doing the partial derivatives, you'll need to differentiate g with respect to its own variable first, and then multiply it by the derivative of that variable with respect to x or y. But apart from that, it's just then a case of carrying out the partial derivatives and feeding it into the expressions to get the results required. In the first case, a single derivative, in the second case a double. So here it is then. Z is expressed in terms of this, and G is expressed in terms of this, which I could call U, but we'll just leave it as that part. I have to produce that bit to the side. Well, first of all, find the derivative with respect to x. Well, it's a product. So 1 times the rest of it, leave it alone, plus x times, and then the derivative of g with respect to its own variable times the derivative of its own variable. Now it's worth noting again that if you've got 1 over x, and the derivative would be 1 over x squared to save you changing between the various forms. Right, so tidy that bit up, and we've got that, and this will be a minus because the negative over there. It'll just be a single x g dashed of y over x. Right, so that's the derivative with respect to x, so I can feed it into that. Now differentiating with respect to y, same again. Again, I've got a product, so it's going to be, first of all, differentiate that and leave g alone, and then the second time leave that alone and differentiate g, again with respect to itself, times its own derivative, which is 1 over x. Tidy that lot up to give this, and that'll knock out the x, and it'll just be y to the 4 g dashed of that. Call that 3. Now, you've got to feed that back in. So we have x times that and y times that one. So x times all the things in 2 and y times all the things in 3. Right, x times this first. Here we go. xy to the 4 gy over x minus x times that is just going to leave me that y to the 5 g dashed y. Now y times this one. So it'll be 4x y to the 4 g of that. Not quite enough room, go here. So plus y to the 5 g dashed y over x. That's fine. Now, those bits cancel out, so there's not a lot left. In fact, they're both the same. They both come to 5. Lots of that, which is the same as the original expression, so that then comes to 5z. So that was easy enough. Right, this bit. Now, to get this second derivative thing, I'm not actually going to use that original expression anymore. I'm just going to work with the derivatives I've got already. So that I'll need another derivative for x and another derivative for y. So first of all, rattle through the whole lot, taking the derivative with respect to x. So there's a product, so it'll be 1 times, and then leave that alone, plus x times now to the second derivative with respect to x. and then that's just the one part, so it'll just be that with respect to x and y, and then differentiate that also with respect to x. There, right, so I've got our first equation, and then that'll form a second one. Now doing the same with respect to y. Well, in this case, that first one, that's got not any y in the first place, so it'll just be differentiated again with respect to y. Notice the y comes down first. That, with respect to y, is a product, so leaving that alone, and now doing the second derivative with respect to y, and then differentiate that with respect to y. There, that's number 3. Oh, so it's hectic. Right, now what I've got to make up this combination. Well, the x squareds should have an x, I'll need another x times it, and the second order derivative, that should need another y, so it should be a y times that one. Right, to form that. Right, so we do that. So x times, where is it, the first one? So that's going to be x times that part, and then x squared for the second term, and then xy for the third term, and then leave a gap for them to add on, and then it'll just be 5x times that derivative with respect to x. Now, third one, times y. So that times y, and of course it's the same both ways round, plus the y times that, plus a y squared, which is just what we wanted, times that, and adding on 5y times its derivative. So I'm just putting out the parts I want on this side, the x squared times the second derivative, they add up to 2, and the y squared times its second derivative. And then 5 take away 1 means it's 4 of them, and 5 take away, where are you? There you are, 4 of them, 1 of them makes 4 of them. Take out the 4 as a common factor, and then, of course, you recognise that part because, whoops, tidy that up, that's the same as number 1. So that's just 4 times, and number 1 was 5z, so it comes to 20z. So there you go, easy marks. Right, now solving a partial differential equation by a change of variable. The change of variable would be necessary to reduce the two partial derivatives to a single partial derivative so you can carry out an integration. Now the problem here is going to be having to change f from being a function in terms of x and y into a function in terms of u and v, which means you'll have to change the partial derivative of f with respect to x into its two parts. The part of f that varies with u times the derivative of u with respect to x, plus the part of f that varies with v times the derivative of v with respect to x, and the same for f. Then after that it's just a case of substituting it in and then carrying out the integration. Now the integration is going to have to involve completing the change of variables. So all the x's and y's are going to have to be changed into u's and v's. And finally, of course, there's going to be some constant left over because only one of the variables was used in the integration. So, right here, so find the solution of that equation using these changes of variables. Right, well, the first thing is going to be this. I'll have to change that in terms of u and in terms of v. So taking that first partial derivative, that's going to be, well, derivative with respect to u times the derivative of u with respect to x, plus the part of f that varies with v times the derivative of v with respect to x. Right, now carry it out. So I don't know what the function is, so I can't put anything down for that, but u with respect to x I do know. That'll be negative 2y over x cubed. F for v I don't know, but I know that v with respect to x will just be 1. So tidy this up, I've got that of the partial with respect to u and just partial f by v. Right, now same again for the partial derivative with respect to y. Well, using these variables, and I know there's no partial there, but it'll be u with respect to v, y, and then even though it's not really there, I'll just put it in for completeness, plus the part of f that varies with v. Right, the first bit, again, I don't know what that function is, but u with respect to y is just going to be 1 over x squared, and that's 0, because v's got no mention of y in it. So I've got that for my other equation. Now I can substitute them both into that. I can put them both into number 1. So 2 plus 3 into 1. So that means I've got x times my first one, so it'll be negative, I'll put it down, negative 2y over, it'll just be x squared, partial by u, plus x times that part, that's it. Then plus 2y times this one, so that's going to give me 2y over x squared. That equals altogether the whole thing. Now clear the top, just so I can write it down from the top. These two parts cancel out handily, or else it wouldn't have worked, leaving me just this single differential. Right, now I'm going to have to start carrying out my change of variables. The change of variables being these two things, just as a reminder. Well, first of all, get that x over out the road. So we've got y to the 2 over x to the 6. So it's the, how do I make it out of this? Well, u squared will give me the y squared with a 4 underneath, another one of them, and that will give me x to the 6 altogether. And then just integrate it, which means f's going to be the integral, keeping u constant, of u squared over v squared. Oh, and I forgot the dv. Right, so that's just going to be negative u, because v squared underneath goes back up to v, plus some constant function in terms of u, since that was held constant. But I want that in terms of x and y, so I'll need to put those variables back the way they were. Well, that was y over x to the 4, and another x underneath makes it over x to the 5, plus some function in terms of, and u was y over x squared. And that's it done. There we go.